Hi guys, we are going to go over your homework. So they were the same as what we were doing in class yesterday. Using this graph, state the value of each quantity if it exists. Keep in mind that if a limit doesn't exist, we say it does not exist. But if a function value doesn't exist, we say it's undefined. All right, part A, the limit as x approaches 2 from the left side. So as you're approaching 2 from the left side, that means we're not going to look at all at the right side of 2. So the limit, what are we approaching? We are approaching 3. The limit as x approaches 2 from the right side, so now we're ignoring the left side of 2, and that limit is approaching 1. Notice that our left side and our right side limit are not equal, so that tells us, that's one way to tell that your limit does not exist. If you're looking at just evaluating the entire limit, remember we don't care what's happening at 2, we care what's happening as we approach it. So if you're on this line and you're walking towards 2, what value are you getting to? And if you're walking towards this line, what are you getting to? If those values are not the same, your limit doesn't exist. Okay, the next part is the actual function value at 2. We need to look at 2 where we have a point. Open circle means we do not include that, so it is actually this one, which is 3. The limit as x approaches 4 of the function. So we are approaching 4, and your limit is coming to also 4. The y value is 4. But the function value is actually undefined because of our open circle there. Okay, so check those over. Okay, number 5 is a similar problem with a new graph. The limit as t approaches 0 from the left side of the function would be -1. The limit as t approaches 0 from the right side is -2. So that tells us that the limit as t approaches 0, so the full limit, it must not exist. And the reason we know that is because from each side you are not approaching the same value. Part D, the limit as t approaches 2 from the right, or I'm sorry, the left side is the first one, and that goes to 2. Okay, as we're walking up this line, you approach 2. Now I know yesterday there was a question of like, well, what do I look at? Because this is a piecewise graph and there's so many different pieces. Whatever number you're approaching, that's the portion of the graph you're looking at. So here we're approaching 2 from the left side. So yeah, you could start all the way out here, but we don't really care what's happening until we get really super close to 2. So same thing with this one, when we're looking at the limit as t approaches 2 from the right side, the positive side, we can start all the way out here, but the only thing that's really going to matter is what happens as we get right in here, when that gap away from 2 is very small. And that's what we started with the other day when we were making those gaps smaller and smaller and smaller with the calculations. So the answer to E then is 0. Again, your left side and your right side limits, they are not the same. Your graph to the left of 2 and your graph to the right of 2 do not meet up, so that tells us that the limit does not exist. The function value at 2, now I need to erase my line so I can actually see what is happening at 2. So limits don't care what's happening at exactly that number, but of course function values do. So at 2, your point is 1. So notice that the left-sided limit, the right-sided limit, the full limit, and the function value are all different, and that's perfectly fine. And then lastly, the limit as t approaches 4, it's the full limit. It definitely exists. It's coming to the same place, and that y value is 3. Okay, now they want us to sketch a graph that hits all of these conditions. The first one, the limit as x approaches 0 from the left side is -1. Okay, so I don't know if this is open or closed with just this information, but what I tend to do is make it close and then open it later if I need to. So making that close from the left side, so I know I'm going to have a line coming off of here. I don't know anything about the right side, but that tells me I have to have a line off there. So I just make one right there, and then later I'll extend it. If they don't give me any further information, I can put it wherever I want. Make the line extend wherever I want. Okay, the limit as x approaches 0 from the right side is 2. Okay, so at 0, I need to go up to 2. Now, because I've already used a closed dot, I have no choice but to use an open dot here. And it's coming from the right side, so I know I have to have some kind of line coming off of here. I don't know what kind of line yet, so I will just leave it like that. Why can't I have a line coming off this left side? Well, if I put a line up there, I would not pass the vertical line test. I wouldn't have a function. Okay, so all we are doing is working with the sided limit that they gave us. Likewise, I'm not going to put a line coming off here because they didn't mention anything about the right side in this first piece. They did here, and that's why I put it on that one. Okay, the last piece is the actual function value at 0 is 1. So that tells me I have a point, 0, 1. Now because of that, that means I have to go back and open this one down here, or else I wouldn't have a function. Okay. Now, at this point, this is not a good-looking graph. I've satisfied all my conditions, but I need to extend these lines because these tiny little short things aren't going to be very obvious that they're lines. So it does not matter at all what you do. If you want to make some kind of curvy, crazy line, if you just want to make a straight line, it doesn't matter, but you need to just extend the graph so it's a little easier to see that those are lines coming off of there. Okay, so your lines might have looked totally different, but you must have an open circle here, a closed dot here, an open circle here, and you have to have some kind of line or curve coming off to the left of this one and one to the right of that one. Okay, one more like that. The limit as x approaches 3 from the right side is 4. Okay, so again, I just tend to start with a closed dot, and I know because I'm coming from the right side, I have to have a line coming over there. I don't know what kind of line, so I make it nice and short, and then I can go back and extend it later. The limit as x approaches 3 from the left side is 2. Again, I've already used an open or a closed point at 3, so the next one I put at 3 must be open. It's at the left side, so I'm going to make a squiggly, small little line coming off of that and see if I get more information later. The limit as x approaches -2 is 2, and that is a full limit. It's not one-sided. So we go to 2. I'm going to go ahead and put a closed point there, although it could be open. We don't really know. It's just that's the easy thing to do. And then because it's a full limit, not one-sided, I know I'm going to have lines coming off of both sides. Continuing on, now they've told us f of 3 equals 3. That was not where either of my limits were, so I have to put my closed point there, which means I need to open the closed one that I already put. Okay. Now, one thought might be, okay, just when you have limits, always keep them open, because a lot of times they give you the function value after, and that's fine. That's totally fine if you want to choose to do that. F of -2 equals 1. I had already put a closed point, or no, that's at 2. Yep, so I need to go and put one here, which means I need to open that one up. Okay, so that's a point there. Now, they didn't give us any information about what line's increasing, decreasing, straight, curved, anything like that. So all I'm going to do is go in and put whatever I want. I'm going to go ahead and make these connect. But maybe your graph goes, so that's one version of a good graph, but maybe your graph goes like that. And that would be perfectly acceptable too, because the key points are still correct. Okay. Certainly, if you guys have questions over any of this when I get back, we can talk about anything you need to. All right, go ahead and get your notes out. We're going to start into the next section. Hopefully I'll be back here shortly and I will interrupt the video and take over. But until then, go ahead and start with these notes. So in section 1.3, our first section, we used graphs mainly and some calculating, those really extended calculator problems where you're plugging in a whole bunch of numbers to see the pattern in order to find limits. What we're going to learn in this section is how to use some properties of limits and then some algebraic methods to calculate limits. All right, these are what are called the limit laws. Suppose C is a constant and the limit as x approaches a of f of x and the limit as x approaches a of g of x, so two different functions. Suppose those limits exist. Then we get the following laws. Number one, the limit as x approaches a of f of x plus g of x is the exact same thing as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So you don't actually have to add the functions first. You can take the individual limits and just add the limits. Number two is that same rule, but for subtraction. So you can take the limit of each function individually and then subtract to get your answer, versus having to subtract the functions first and then take the limit. Number three, the limit as x approaches a of a constant times a function is the same thing as if you take the limit of just the function and then multiply it by the constant. So it's like you can actually kind of take the constant out of it, deal with just the limit of the function, and then go and multiply by the constant. The limit as x approaches a of two functions being multiplied, I imagine you could guess what this is going to be. You can take the limits of each function individually and then multiply those limits. Knowing that, any guesses what the final limit law is here in this list? Hopefully you're thinking division, and that would be correct. So if you have two functions that are being divided that you're trying to take the limit of, you can go ahead and do the limits of the functions individually and then divide those limits. This, of course, would have to have a stipulation because we can't let that denominator be 0. So this is only if the bottom limit, in this case g of x, does not equal 0. Okay, continuing on, a few more. The limit as x approaches a of some function that's raised to an exponent is the exact same thing as taking the entire limit of the function, taking the limit first, and then raising that to the same exponent. And we should say what n is, where n is a positive integer. Okay, so you can either, on the left side, evaluate the function to the exponent and then take the limit, but it is equal to what's on the right side, taking the limit of the function and then raising the limit to the exponent. The limit as x approaches a of a constant number is just the constant number. Think about a graph of this. What's the graph of a constant number look like? Like that, right? So no matter where we take the limit, whether x is 1, 2, 3, 4, -1, -700, it doesn't matter. The y value is always whatever your constant value is. The limit as x approaches a of x equals, well, let's think about this one. The function is literally x. The graph of x looks like this. So I'm getting crooked. Think about what you know about the ordered pairs on this line. Your equation's y equals x, so this would be the point 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, -1, 1, -1, -2, -2, -3, -3. So if you're approaching a, whatever a is, the y value is also a. Okay, number 9. The limit as x approaches a of x to, now we're not going to take just x, but we're going to take x to the nth power. That is going to be a to the nth power. Okay, and then a similar law holds true for roots or radicals as well. If we take the nth root of x, then the limit is just the nth root of a, whatever you're taking the limit towards. And then you can kind of generalize that one step further. The limit as x approaches a of the nth root, not of x, but of any function, is the same thing as the nth root of the whole limit of the function. So what I'm looking at is rule number 6 and rule number 11 are basically the same thing, because we know a root can also be written as an exponent, but number 6 they had specified it's an integer, and this would not be an integer. So that's why we have it as an additional rule. All right, I'm going to stop here. If by chance I am not back, just hang tight, and then we're going to go a little further here.